Since a sharp edge is weak and fractures easily, an insert's cutting edge is prepared with particular shapes to strengthen it. Those shapes include a honed radius or rounding on the corner, a chamfer to break the edge, a land or small negative slope, or a combination of the three. A fine finishing insert may need only a small edge rounding, while a heavy roughing insert may have a significant negative land for edge strength. The drawback of negative lands is that they need more power and alter chip formation unfavorably. Super hard tool materials are divided into two categories: cubic boron nitride and polycrystalline diamond. Typically, a small tip of one of these super hard materials is bonded to a carbide insert base. Super hard inserts may cost 30 times more than a carbide insert, so their use is limited to well-chosen, cost-effective applications. Cubic boron nitride, or CBN, the second hardest material after diamond, is used to provide long tool life in machining very hard, tough ferrous materials, hardened die steels, alloy steels, and hard-facing materials. CBN is a hard, brittle material requiring cutting-edge preparations to suit application needs. Other techniques are utilized to protect the cutting edge, such as the use of a lead angle, where possible, and a strong shape, such as round or square, are recommended. Polycrystalline diamond, or PCD, is composed of micro-sized diamond particles in a metallic binder and is over 50 times harder than common carbide. PCD is used for non-ferrous applications and also cuts abrasive materials such as glass, reinforced plastics, and hardwoods for furniture manufacturing. Cutting functions actually affect chip formation and influence cutting tool life, chip removal, and surface integrity. The life of the cutting tool is directly affected by the type of cutting fluid and application process used. The choice of fluid also plays a role in effective chip removal. The cleaner the fluid is, and the faster the chip leaves the cutting zone, the longer the tool life, and the better the surface integrity will be. Surface integrity refers to the quality of the material after machining. How well the fluid reduces friction and carries away heat can have a major effect on the surface integrity of the piece part. Because of the heat and stress generated by some cutting processes, the material may be altered chemically, physically, or experience electrical and magnetic changes.
The first step in production is sawing. And depending on tolerances, no further processing may be necessary. TCI's precision saws hold tolerances to plus or minus 5 thousandths. For many applications, this capability allows customers to go right to work, machining blanks as they arrive in the door. Band, plate, and radial saws with programmable controls and automatic feeds make short work of precision sawing requirements, including plate, cutoff, miter, and contour sawing. Start saving today.
All right, today I'm going to show you how to center drill, and countersink your part using a drill chuck on a milling machine. We could do this on a drill press if we wanted to, but if your print calls for an exact location of this hole in your part, it's best to do it on a Bridgeport mill using the assistance of a DRO, and make sure always that you lock your table locks down, your saddle lock down, and your knee lock down, so that your table and your vise doesn't move. So now we've already positioned it in your X and Y. So you take your center drill, put it in the drill chuck, tighten it up, turn on your spindle, drop it down and center drill your hole. Just like that. Turn your spindle off, hit your brake, loosen it up, take your number 7 drill bit, take it chuck, tighten it up, turn on the spindle, just drill your part. Now if this was steel, stainless steel, or any exotic type metal, we would use coolant, but for this video today, we're using plastic, so I think we can get away with no coolant. Take your chuck, wrench, loosen it up, and you just take your countersink, tighten it up in your chuck, turn on the spindle. You just want to kiss the top of your part. Now, just open the chuck. Like that. Now you have a center drill, and tap hole in the exact location.
The drill point, which does the work of metal cutting, is formed by the 2 cutting lips and the chisel edge. The cutting lips, when the drill is correctly ground, form 2 straight lines connected by the chisel edge. The length of the chisel edge depends on the angle it makes with the cutting lips and the thickness of the drill web, or core. The web thickness at the drill point is a compromise between thick for rigidity and thin for rapid penetration rates, larger flute space, and good chip clearance. The standard drill point commonly has a 118-degree point angle, symmetrical cutting lips, and a clearance angle typically between 10 and 20 degrees.
To create a countersink for our rivets in thicker materials, such as 63 thousandths and thicker, we cannot dimple, but rather machine countersink. This process actually removes metal with the cutter to make room for the rivet, as opposed to dimpling where the metal is simply deformed. Here's what our countersinking tool looks like. It is driven by our drill. Notice at the tip of the cutter is a pilot which we will insert into the rivet hole to be countersunk. We need to have a different cutter so that the pilot matches each of the popular size rivet holes we drill. The cutter will spin and cut the metal at a 100-degree angle, which coincides with the angle of the rivet heads. The cage provides an adjustment to make sure we don't cut too far or too little into the metal by limiting the depth of the cutter. Twisting the adjustment in one direction allows the cutter to protrude a little bit farther, the other direction a little bit less. Let's demonstrate how this works. We first drill and deburr the hole. Assuming we have properly adjusted our cutter, all we need to do is spin the drill and press all the way down. It is very easy to cut too little or too far into the metal, which will adversely affect the fit of the rivet. Cutting too little will not allow the rivet to seat flush. Cutting too far provides for a sloppy fit. Experimentation is essential in getting just the right cutter depth.
Hello, this is our light-duty Cutmaster 12 by 36 inch lathe with a 1.5 inch spindle hole. Stock number 1660. Here, the Cutmaster is taking a 50 thousandths cut per side on a 2 inch diameter bar of hot rolled steel. Now the Cutmaster is drilling a 1/2 inch diameter hole in hot rolled steel. The Cutmaster is now cutting an 1/8 inch wide groove in hot rolled steel. The Cutmaster features swings of 12 inches over the bed, 7 inches over the cross slide, and 17 inches in the gap. The Cutmaster has a 1.5 horsepower 220 single phase motor with 9 spindle speeds of 70 to 1400 RPM. This model comes equipped with the following: 6 inch 3-jaw chuck, 8 inch 4-jaw chuck, 10 inch face plate, 3 inch steady rest, and 4-way tool post. Thanks for watching. Give Industrial Machinery a call. Our number is 614-464-4376.
In straight turning, the tool is fed parallel to the axis of the work to reduce its diameter so that the final diameter is the same at each end. Removing a significant amount of material in one pass is called rough turning. The final lighter cut that creates a smooth surface finish is called finish turning. Taper turning produces a taper along the axis of the workpiece. Tapers are produced by offsetting the tailstock from center line or by using a taper attachment. Short, steep tapers can be turned using a compound rest. Contour turning, or profiling, was formerly performed by having the single-point cutting tool trace a template of the desired profile shape. This has largely been replaced by CNC turning, in which the desired contour is simply programmed into the machine, which directs a cutting tool to cut the contour. Forming is another alternative for generating complicated shapes. The tool having the desired form or geometry is advanced perpendicular to the axis of rotation, reproducing the tool shape in the workpiece. Forming is commonly performed on automatic screw machines. Chamfering eliminates sharp corners from a workpiece and is a good safety measure. Typically, chamfering breaks corners at a 45-degree angle. Grooving creates a groove or recess using a tool that is usually the size and shape of the required groove. Some grooving tools can also widen a groove by traversing side to side after plunging into the workpiece. How much a tap cuts per revolution depends on the angle at which the cutting tooth on the die contacts the workpiece metal. This is called the rake or hook angle and is defined as the angle between a line through the center face and a radial line from the tool center to the tooth tip. Generally, the more ductile the materials, the greater the rake angle, because the die tooth can take a bigger bite out of the softer materials. Tapping speed is critical in determining how a tap cuts, because it affects thread quality and tap life. Too much speed causes the tap to dull, break, or tear up the metal. High-speed tapping also makes it difficult to achieve good lubrication and chip removal. For For softer metals, or where it is important not to make chips, thread-forming taps or roll taps may be used. Roll taps have no cutting edges or flutes. They generate more frictional heat than standard taps, since they form rather than cut the thread. Broaching is the fastest method of machining gears and is performed on many different machine types using a multi-tooth cutting tool called a broach. The broach or the gear blank are pushed or pulled relative to each other to remove material. Each tooth on the broach is generally higher than the preceding tooth. As a result, the depth of cut increases with each tooth as the broaching operation progresses. The conventional method of broaching is used mainly to produce internal gears. For external gears, pot broaching is used. Pot broaching is performed on special machine tools having a hollow broaching tool assembly called the pot. Gear blanks are either pushed down, pushed up, or pulled up through the pot to generate the gear teeth. Milling edges, shoulders, and grooves may use a combination of end, peripheral, and/or face milling operations. Creating edges or edging may involve the milling of one or two surfaces. Shoulders typically have two surfaces, and grooves usually have three surfaces. Grooves may be closed at one end or open at both ends, and they may be cut on internal and external flat surfaces as well as on round surfaces. Peripheral milling cutters have cutting edges on their periphery, which are parallel with the axis of rotation. Peripheral milling is useful for creating long open slots and forms. End milling cutters are round shank tools with cutting edges on their periphery and end. The axis of rotation is perpendicular to the surface produced by the end of the tool. Cutter size is defined by its diameter and cutting depth. Since end mills cut more with the teeth on their periphery than with the teeth at their end, they are susceptible to lateral forces. This makes them subject to deflection, which reduces the accuracy of the milling operation. Short, shallow slots are often created with end mills. Deep, narrow slots may be milled with an end mill, a thin slitting cutter, or a grooving cutter. Grooving or slotting cutters are generally more efficient than end mills for cutting long and deep slots because of their larger diameter and greater number of teeth.
Thank you for taking the time to view the exclusive CNC Junior tabletop milling machine engineered and manufactured by CNC Masters Incorporated in the USA. CNC Masters prides itself in offering high-quality CNC milling machines at competitive prices. Thousands of satisfied customers in the USA and around the world are enjoying the numerous uses of the CNC Junior milling machine. Because of its unique turnkey design, the CNC Junior mill allows the novice user who is entering the world of CNC for the first time and the experienced user to quickly gain control and master the operating features of the CNC Junior mill, saving the user valuable time. This is especially important if the user is under pressure to quickly prototype a part or has promised customers a quick turnaround, whether it be secondary operations, prototyping, or even mass producing a part for a client with materials as soft as foam, wax, plastic, and wood to as hard as aluminum and even titanium and steel. In just a matter of minutes, any user who is familiar with a PC mouse can quickly figure out how to use the CNC Junior mill without on-site training. With travels such as 19 inches on the X, 7 inches on the Y, and 5 inches on the Z, the CNC Junior can meet several machining applications within those parameters. Unlike other CNC milling machines, the CNC Junior does not require any advanced technical setup of the controller and software. Overall, the CNC Junior is a robust, mid-size milling machine, automated system designed for the user who needs easy-to-use features and desires to design 2- or 3-dimensional applications immediately. You can jog your axes with the touch of your PC mouse, keyboard, or optional handheld remote control. You have feed control, relative control for exact driving distance of each axis, optional coolant control, and optional spindle speed control as well. The CNC Junior is a versatile machine with X and Y precision preloaded ball nuts with anti-backlash ball screws for precise machining of parts, detailed fine engraving with our engraving attachments, and has true 4th axis optional control as well. The CNC Junior can accept simple English commands for quick and easy toolpath programs, or if you are cutting complex parts such as these, the Junior can accept G-code files from popular CAD/CAM softwares as long as the user obtains the proper post-processors from them. In this demonstration, we are showing a complex acorn, 3-dimensionally shaped part of a mold being machined from a G-code file generated from a popular CAD/CAM software. You will note the complexity of this design by its many circular patterns in the horizontal and vertical planes. Using aluminum, this part is machined in 3 separate programs, about 2 hours and a half altogether. The first program is a roughing tool path using a 1/2-inch flat cutter. The second program requires a 1/4-inch flat cutter for a finish roughing, and the last program will complete and finish the part using a 1/4-inch ball cutter. But for the sake of time, we are phasing in and out to show you significant advances of all 3 programs as the CNC Junior machines the part, noting the accurate interpolation of its 3 axes. If you are interested in the CNC Junior mill, we would love to earn your business. Please feel free to correspond with us at sales@cncmasters.com or call us on our toll-free number located on our website should you have any questions or would like to receive a quote. We know time is money, and our staff is committed to providing email or phone support in a timely manner should the need arise once you place an order with us. We aim to take our after-sales support just as seriously as trying to earn your business. Again, we thank you for taking the time to view the CNC Masters CNC Junior Mill, and we hope that we can meet your machining needs without breaking the bank.